Okay, I'm now recording. Okay, so we're going with the homework. Reminder, second exam is on December 9th. Review for the second exam is on December 7th. Questions about homework 8. This is 6.2.3, number 2 from homework 8. Second exam is on December 9th. Reminder, review for the second exam on December 7th. Okay, this is the second problem from homework 8. So I copied and pasted here from the assignment. So we have to determine whether or not this is a fair game. Okay, a balanced size rolled until the same result appears twice. Okay, so what is the probability? Let's say that a 1 appears twice in less than, well, oh, wait, okay, so in less than 6 rolls. In less than 6 rolls. So at most 5 rolls, you want a number to appear twice. Well, the first time you roll it, you get any number. When you roll it again, in order for okay, so in order for the probability that a number appears twice in 2 rolls, okay, is then, well, the first one could have been anything. But then you multiply it by 1/6, the probability that it's the same as the first roll. So there's a 1/6 chance that the number appears twice in 2 rolls. Okay. Now the probability of a number appears twice in 3 rolls. Well, the first roll could be anything. But then after the first roll, the second roll can't be the same as the first. There's a times 5/6 chance of that happening. It's any 5 of the 6 that was different than the first. Now the third roll can be the same as any of the first 2. It's a times 2/6 chance that's the same as the first 2 different rolls. And so if you multiply those 2, you get 10/36. That's the probability that the number appears twice in 3 rolls. The same number appears twice in 3 rolls, and the probability the number appears twice in 4 rolls, and that takes 4 rolls, is, well, 1, you can roll anything the first time, times 5/6. It has to be different than the first one. Now the next one has to be different than the first 2. There's a 4/6 chance of that. And then the fourth roll has to be the same or 1 as the previous 3, so that's times 3/6. And so this is 60 divided by 6 cubed, which is 216. And so that's the same as 10 divided by 36, which is the same as 5/18. Okay, now the probability that the number appears twice in 5 rolls, because it has to be less than 6. In 5 rolls, the first time anything, the second time has to be different. So 5 times 5/6. The next one has to be different again, times 4/6. The next one has to be different again. So it's 3/6. Those are 4 rolls. The next one has to be the same as one of the previous 4, so that's times 4/6. And so you multiply those probabilities, and you get 240 divided by 6 to the 4th power. Okay, and so I'm going to divide by 6. So that's 8, 24. That's 80/6 cubed. So this is 80 divided by 216. And so you can simplify that. That's so you divide by 8. And so you get, this is 20, so 8/16, 27, I think. So times 8, 160, 56, 260. So 10/27. That's the chances of probably appearing. Probably number appears twice in 5 rolls. And so, okay, so is this a fair game? So, so the expected value here is going to be, so let x equal the amount that player A pays player B in one game. Okay, so E of X is going to be the sum of all possible values of X times F of X. So what are all the possible values of X? Well, so here, the probability that the number appears twice, this is equal to the probability. Well, if it appears twice, A pays B, so that would be probably X equals 2. The probability that player A pays player B $2, one for each of the two roles. Okay, now this is probably X equals 3. This is the probability X equals 4. This is the probability that X equals 5. Otherwise, player B pays player. Otherwise, player B pays player A $25. So that would mean that X equals -25, because the act of B giving A 25 is, I'm going to say the opposite. A gives B -25. So that probably X equals -25, which is 1 minus the sum of all those probabilities. 1 minus the probability that X is equal to 2, 3, 4, 5, or 5. Okay. So this is 1 minus the sum of those probabilities there, which is 1/6 plus 10/36 plus 5/18 plus 10/27. Okay. So that's the probability that X is equal to -25. So the expected value of X is taking each value of X and multiplying it by its probability. So 2 times 1/6 plus 3 times 10 divided by 36 plus 4 times 5/18 plus 5 times 10 divided by 27 plus, and then X could be -25, and then it's times that probability there. Okay, so so this is equal to, really quickly, use my calculator. So you have 1/6 plus 10/30. Okay. Plus 10 divided by 36. So that's good. Plus 9 divided by 18 plus 10 divided by 27. Wait a minute. 1/6 10/36. 60/216. 10/36. 5/18. 240/6 to the 4th. This is a 40. That's why. It's 40, 40. Okay, so that's equal to 40/216, which I don't want to spend the time simplifying, so I'm going to write 40/216 here. Okay, so then that's it. Okay, so now it's 1/6 plus 10 divided by 36 plus 5 divided by 18 plus 40 divided by 216. Okay, so this is equal to 1 minus 0.9074. That's equal to 0.0926. Okay, so that's the probability of that. So what number goes here is 0. 0.0926. Okay, and so then you so you have 0.0926 times -25 plus everything else. And so that you get a negative number, you get negative 0.0372. Okay, so the expected value is negative. So this is not a fair game. Okay, so the expected value is negative. So the amount that player A pays player B is negative. And so you'd rather be player B. I mean, you'd rather be player A because the amount that A is giving is negative. I mean, A is getting money. So you'd rather be player A. And so the expected net gain per game. So player A's expected net gain per game is 0.0372 or about 4 cents per game. Okay, does that answer the question?
Yes, thank you.
Okay, so let's keep going. Any other questions? Okay, let's keep going. So last lesson ended with 6.3.2, which is on the mathematical expectation of a function of a random variable. So we gave this definition of expected value, okay, of a function of a random variable. Okay, and so we have these two conditions: whether x is discrete or x is continuous. Provided that the series converges absolutely in the discrete case, and provided the integral is defined in the continuous case. So I'm going to start this class with an example. Example 6.16. Let g of x be the random variable of example 6.14. Find the expected value of g of x. Okay, so in example 6.14, we just had the S is the experiment rolling 2 fair die, and S X is the sum of the values of the 2 dice. Okay, so that's our random variable there. And g of x is equal to x squared. So it's this g is x squared, x is the sum of the 2 dice. Okay, so we want to find the expected value of g of x. So the goal is to find the expected value of g of x. So E of g of x is equal to the sum over all possible values of x of g of x f of x. And so that's equal to the sum. Well, x, the sum of the values of the 2 dice, right? And so the possible values of x are, so if we add 2 dice, the smallest sum it can be is 2, 1 plus 1 is 2, and the largest sum is 12, because you have 6 plus 6, which is 12. So all the numbers in between also happen. So the possible values of the sum x are 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So it's the sum from x equals 2 to 12 of x squared, which is g of x, times f of x. Okay, so I just substitute g of x for what it is, which is x squared, and I'm considering the sum from x equals 2 to 12 because they're all the possible values of x. Okay, so this is equal to, well, you just plug in each number and calculate. So the first one is 2 squared times f of 2 plus, and f of 2 is 1 over 36. Okay, plus 3 squared times the probability the sum is 3, which is 2 over 36. Plus 4 squared times the probability the sum is 4, which is 3 over 36. Plus 5 squared times the probability the sum is 5, which is 4 over 36. Right, so you see the pattern. 6 squared times the probability the sum is 6, which is 5 over 36. Plus 7 squared times the probability the sum is 7, which is 6 over 36. That's the most likely sum. Plus 8 squared times the probability the sum is 8, which now starts going down again, 5 over 36, plus 9 squared times the probability that the sum is 9. The sum is 9, and it's 4 over 36, plus 10 squared times the probability the sum is 10, which is 3 over 36, plus 11 squared times the probability the sum is 11, which is 2 over 36, plus 12 squared times the probability the sum is 12, which is 1 over 36. So you take the sums of those products and you get 1,974 divided by 36. And that's equal to 54.83. Okay, and so that's the expected value of g of x. So the next section is on theorems on mathematical expectation. Okay, so the first theorem is theorem 6.3, which says if c is a constant, then the expected value of the random variable, constant random variable, is equal to that constant c. Okay, so the proof of that is that if you take the expected value of c, well, it's equal to the value c times the probability that capital C is equal to the value little c. Well, that's c times 1, because it's always c. So this is equal to c. So that's it. Okay, theorem 6.4 is let a naught, a1, a2, so forth, up to including an be constants. If the expected value of x, expected value of x squared, up to including the expected value of x to the n exist, then if you want to take the expected value of the polynomial a naught plus a1 x plus a2 x squared plus dot plus a sub n x, the n, this is equal to a naught plus a1 e of x plus a2 e of x squared plus dot plus a sub n e of x to the n. Okay, and so you have that equation. Okay, and a corollary of this theorem is that if a and b constants, then the expected value of ax plus b is equal to a times the expected value of x plus b. Right? Because then you just take e of ax plus e of b is b, and e of ax is A times E of X. So you have that as a direct correlate of that theorem. Okay, so once we have theorem 6.4, we have that corollary. Now to prove the theorem 6.4, let G of X equal to that polynomial A naught plus A1 X plus A2 X squared plus dot 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 plus A sub n X to the n. Then then the G of capital X is going to equal this. It's going to be the random variable, where you just have your random variable X here. Say X, capital X for the random variable capital X. Okay. And you have that the expected value of this by substitution is equal to the expected value of G of X. And the expected value of G of X is equal to the sum over all possible values of X, G of X, F of X. And so this is equal to the sum over all possible values of X of this polynomial times F of X. Okay, so now we have G of X here, and so G of X is this, and you're multiplying it by F of X, and you're summing over all possible values of X. So now we separate the terms, and so we have the sum over all possible values of X of, so we have A naught times the sum over all possible values of X of F of X plus A1 times the sum over all possible values of X of X F of X plus next term would be A2 times the set sum times X squared F of X plus dot 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 plus A sub n times the sum over all possible values of X to the n with F of X. It's now it's equal to that. Okay, and this is equal to A naught. Well, this is E. It's just A naught. Because if you take the sum over all possible values of X of F of X, this sum is 1. So you get A naught there times 1, which is A naught, plus A1 times E of X, because this sum is X. This is for X. And then plus A2 E of X squared, which is you sum over all possible values of X squared. F of X, that's the expected value of X squared. It's plus dot 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 plus A sub n E of X to the n. All right. And so we just showed is that the expected value of this is equal to that sum. And that's what we wanted. We wanted to show that this was equal to this. Okay, and so we are now done with that. So in example 6.19, we let X be the random variable of example 6.2. Find the expected value of 3 minus 2x and the expected value of x plus 4x squared. Okay, so for example 6.2, in example 6.2, x is discrete with probability function f of x is equal to one third for x equals 3, and 2/3 for x equals 9. Okay, so now we found that the expected value of x is equal to 7. So what we want to do is we want to find e of 3 minus 2x and e of x plus 4x squared. Okay, so e of 3 minus 2x is equal to 3 minus 2 e of x from our previous theorem, this theorem. Okay, so we have that. Okay, this is equal to 3 minus 2 times e of x, which is 7, which is 3 minus 14, which is negative 11. So that's e of 3 minus 2x. Okay, so e of x plus, this is equal to e of x plus 4e of x squared. And so e of x we know is 7. So it's 7 plus 4 times e of x squared. And so we just need to find e of x squared. So we find e of x squared. And so e of x squared is the sum over all possible values of x squared times f of x. And so the two possible values are, well, 3 squared times the probability of x is 3, which is 1/3, plus 9 squared times the probability x equals 9, which is 2/3. And so that's 3 plus 54. And so that's 57. Okay, so e of x squared is 57. So this is 7 plus 4 times 57. So this is equal to 7 plus, it says 228. And so that's equal to 235. Okay, so we found e of 3 minus 2x is negative 11, e of x plus 4x squared, which is 235. So that's the end of 6.4. And now this is 6.5. And this is the variance and standard deviation of a random variable. Okay, so this is definition 6.4. Variance of a random variable x with mathematical expectation mu is variance of x, that's notation for it, is equal to the expected value of x minus mu squared. So the expected value of x minus mu squared, provided that the expected value of x minus mu squared exists. Okay, so the next definition is definition 6.5, which is the positive square root of the variance of x is the standard deviation of x. Okay, so we have the standard deviation of x. And so that's the positive square root of the variance of x. And this is the definition of the variance. Okay, it's the expected value of x minus mu squared. That's the variance. And that standard deviation is the square root of that. So that's those two. Notes that the standard deviation, that's short for standard deviation of a random variable. That's short for random variable. So standard deviation of a random variable, capital X, is often denoted by sigma. And the variance of X is denoted by sigma squared. Okay. So in example 6.20 refers to example 6.1. So in example 6.1, so 6.1 was rolling a fair six-sided die. Yeah, so it's just rolling a fair six-sided die and recording the outcome of that one roll. Okay, so right, so the possible values of X, where X is the result of the dice roll, and so X could be equal to 1, 2, 3, 4, 5, or 6. So those are the possible values. Okay, so if we want to find the variance of X, it's equal to the expected value of X minus mu squared. So when you compute the expected value, you already have that the expected value of X is equal to 3.5, right? So you can calculate it and it's 3.5. So this is the expected value of X minus mu squared, where mu is the expected value, which is 3.5. So mu, remember, is the expected value, which is 3.5. So you want the expected value of X minus 3.5 squared. So that's equal to the sum over all possible values of X, which is from X equals 1 to 6, of X of the expected value of X minus 3.5 squared. So you have X minus 3.5 squared times f of X. Okay, so you just take each possible value of X and you plug it in and you get a product. And so you add up each product, you add up the products, and then you get the final answer. So it's 1 minus 3.5 squared f of 1 plus 2 minus 3.5 squared f of 2 plus 3 minus 3.5 squared f of 3 plus 4 minus 3.5 squared f of 4 plus 5 minus 3.5 squared f of 5 plus 6 minus 3.5 squared f of 6. And so this is equal to, so the probability of each number is 1/6. So for each of these values, you just plug in 1/6. Yeah. So f of 1 is 1/6. F of 2 is 1/6. F of 3 is 1/6. F of 4 is 1/6. F of 5 is 1/6. And f of 6 is 1/6. You just plug in the 1/6 there. And so when you compute the sums of those products, you get 175 divided by 60, which is 2.97. And so that is the variance of X. It's just the sum of all possible values of X minus 3.5 squared f of X in this example, because the expected value is 3.5. Okay. The next example is example 6.21. And so in this example, we calculate the variance in example 6.4. So we want the variance in that example. So in example 6.4, let's just do example 6. Let's do example 6.22, which is the variance in example 6.3. So this is, so the variance of X. Okay, so in example 6.3, we had X is a continuous random variable with probability density function X, which is equal to (81) X squared, or 0 less than X less than 1/3, and 0 elsewhere. Okay, and so okay, so we want the variance for that example, and we found that the expected value of X was equal to 1/4. Okay, so we want the variance of X, which is the expected value of X minus mu squared. So that's equal to the expected value of X minus 1/4 squared. And so this is equal to, because it's a continuous random variable, we're integrating. So we're going to integrate from negative infinity to infinity of X minus 1/4 squared f of X dx. Okay, so you just find that integral. Now, in this problem, the PDF only is non-zero between X. X is from 0 to 3. So when we integrate this, we only need to integrate from 0 to 3. And so X minus 1/4 squared and times f of X, which there is 81X squared dx. If you calculate the integral, you get 0.00417. So the variance of X there is 0.00417. Okay. All right, so that's another example. Okay, so next is section 6.5.2, which is the variance as a measure of dispersion. Okay, so the variance of X is the mathematical expectation of the random variable X minus mu squared. So it is the expectation of the square of the deviation from X. I said square of the deviation, square of the deviation of X from the mean of X. Thus, the variance may be looked at as a measure of dispersion. Okay, so it's the expectation of the square of the deviation of x from the mean of x. And so it can be looked at as a measure of dispersion, how far away x is from its mean. Okay, so if we look at the whiteboard, go to the whiteboard, I'm going to draw a graph of the PDF of, so let me just go to this picture. So, okay, so if you have this and you have this, let's say mu is here. You have mu minus delta here and mu plus delta here. And so you have here and you have here. So you have 68.3%. So approximately 68.3% of the area under the curve of a PDF lies within one standard deviation from mu. Okay, so if this is your PDF, you graph PDF of your continuous random variable, then 68.3% of the area under that curve will be between mu minus delta and mu plus delta, where delta is a standard, is the standard deviation of a random variable. So delta is the standard deviation of your random variable. Okay, mu is the mean, E of x. Okay, now if you keep going and you go out to mu plus 2 delta, I mean, not that, sigma. This is sigma. U minus sigma, mu plus sigma. So that's sigma. Is standard deviation sigma, mu is the mean. Okay, so if you're one, at most one standard deviation from the mean, the area, 68.3% of the area under the curve is within one standard deviation from the mean. Okay. Now, if you keep going out, another standard deviation away. Okay, so now if you have another 13.6% here and another 13.6% there. So that's the percentage of the area in this region. Okay, so each of them is another 13.6%, and so they add up to another 27.2% of that. Okay, if you looked at the total amount of area going from here to here, it would add up to, so you have 27.2, you have about 95%. But technically you have 95.5%. Okay, and then if you look at the next region, so if you go out to another standard deviation away, mu plus 3 sigma and mu minus 3 sigma. Yes, Kashan?
So the pink is the area under the curve. The pink area.
The curve is the PDF, right? So we're talking about the area under the PDF.
No, I'm saying that the 68.3 is like the area under the curve. Like
that's the percent of the total area under the curve.
Oh, okay.
Does that make sense?
Yeah.
Okay, good. And so then, right, and so then these are the percentages of these other parts. So you have 95.5% within mu minus 2 sigma and mu plus 2 sigma. And then if you go out another standard deviation away, you're adding another 4.2. So then you have 99.7% here. So 99.7% of the area is between mu minus 3 sigma and mu plus 3 sigma. And then the rest of it is outside of that. And so this is about, so this is 0.15%. And this is 0.15% here. Okay, and so that's the percentage of area in this remaining part. It's very small parts. It's not quite drawn to scale. Okay, so okay, so you have your PDF, and then these are the areas, the percentages of the area under the curve, as far as how far away you are from the mean. Right, the mean is here. It's that point there. That's a vertical line. Okay, good. Okay, so that explains that. I think it's clear from the picture. Okay. Oh, okay. Okay, good. Okay, so 6.5.3 is on relating the variance of a random variable to the variance of a set of numbers. Okay, so variance of a set, capital A, which is equal to the set A1, A2, dot, 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 A sub capital N, of not necessarily distinct numbers. So those A's could be repeated as the same numbers. So the variance is equal to the fraction. So the denominator is capital N, and the numerator is the sum from I equals 1 to capital N of A sub I minus the average of the A's, which is denoted by A bar squared. Well, the mean. A bar is the mean. This is where A bar is equal to the sum of all the A values divided by capital N. So if you add up all the A's and divide by capital N, the number of A's, that's the mean, that's A bar, and this quantity is the variance of that set. Okay, this is the mean of the set. Okay, so note that after some calculations, you can get that this quantity is equal to, so you would, in the numerator, what you could do is you could expand out the numerator. So instead of AI minus AI bar squared, you could expand that. You could get AI squared minus 2 A sub I A bar plus A bar squared. This is equal to the sum over capital N of this. So then you have the sum from I equals 1 to capital N of a sub I squared minus the next term, which is 2 a bar times the sum from I equals 1 to capital N of a sub I plus capital N in the denominator, and you have a bar squared plus, oh, well, the sum, which is, so if you have the sum, you have the sum, not you have the sum of a bar squared here. Now the sum of a bar squared, you're adding n, capital N of them. I ranges from 1 to capital N, but it's the same term each time. So you're just adding capital N of them. And so the result of this sum is just that you get capital N of those. So instead you have capital N times a bar squared. And so this is equal to, so you have this quantity here. You want to simplify it. The first term you can keep like that. You have this. Now this term is a bar. So you have another a bar here. And so here the n's cancel. So you just have that. Right? So that's a bar squared. And so now this is equal to oh, okay, wait. So then if you the sum, this fraction, the sum over capital N is a bar. So this goes away. Okay, and so then you have plus n bar squared. Okay, so the sum of the a's over capital N is a bar. So you have 2a bar times a bar here. So this is a bar squared. So you have minus 2a bar squared plus a bar squared. And so this is equal to this sum minus an a bar squared. Okay, because you have 2a bars minus 2a bar squared plus a bar squared, which is minus a bar squared. Okay, so the possible values of x are the distinct numbers in set capital A, which we denote as x1. We denote here as x1, x2, xn. Denote here as that. Okay, so so the probability that x equals one of those values, x sub I, that's f of x sub I. So what's the probability equals that? It's k sub I over capital N, where k sub I is equal to number of elements of capital A that are x sub I. So it's the frequency of x sub I, k sub I divided by capital N. That's f of x sub I. Okay, so now you have sigma squared, which is equal to the variance of capital X, which is equal to E of x squared minus E of x squared. And so this is equal to the sum over all possible values of x squared f of x minus the square of the expected value of x, which is the sum over all possible values of x f of x. Okay, and so this is equal to the sum over all possible values of x of okay, so instead of all possible values of x, I'm going to write x of I, and I is going to range from 1 to n. Okay, so I is going to be index for the possible values of x. Remember we said the possible values of x, the possible values in set A are x1 to xn. So I'm going to index them by that. And so, okay, so you have x sub I squared times f of x sub I, which is k sub I divided by capital N. This is minus the square of that mean, which is this sum. But instead of, so, which is again k sub I divided by capital N. So now you have that. And so this is equal to the sum over capital N. The sum from I equals 1 to capital N of a sub I squared. Because you're just taking each possible value of x sub I, squaring it, and then multiplying it by the number of times x sub I appears in the set. Equivalently, you could just add up the squares of all the a sub i's. And so this is minus the square of the fraction, where the denominator is capital N, and the numerator is the sum from I equals 1 to n of a sub I. Because instead of just taking each possible value and multiplying it by the number of times it appears and adding that, you can just add all the values in the set, even if they're repeated. So this is divided by capital N. Okay, this okay, and so then this is equal to the sum from I equals 1 to capital N of a sub I minus a bar squared. Okay, good. Okay, so then okay, and so you can do you get the same value. Okay, so then, and this is equal to the variance of the set capital A. Okay, so what we showed is that we showed the variance of the set A is equal to this quantity. Okay, we got this quantity as the variance. Okay, so the variance is this sum divided by capital N. Okay, so if capital X is the value of the element selected from set capital A randomly, then the variance of capital X equals variance of the set capital A of numbers. Okay. Okay, so the next section is 6.6. That's on theorems on variance. Okay, so we have theorem 6.5, and it's the variance of X is equal to E of X squared minus E of X squared. Okay, note that another way to write E squared of X is used to denote E of X, the square of E of X. Okay, so E squared written like this, that means squaring E of X. Okay, so the proof. So by theorems 6.2 and 6.3, we get that the variance of X is equal to the expected value of X minus mu squared, which is equal to E of X squared minus 2 mu X plus mu squared. So I squared X minus mu, get X squared minus 2 mu X plus mu squared. And so this is equal to E of X squared minus 2 minus plus E of negative 2 mu X plus E of mu squared. Okay, and so this is equal to E of X squared minus 2 mu E of X plus mu is a constant. So the expected value of a constant is that constant. So this is plus mu squared. And so this is equal to E of X squared minus, well, E of X is mu. So this is 2 times mu squared plus mu squared. And so this is equal to E of X squared minus mu squared. Okay, so that's E of X squared minus E of X squared. And so another way to write it, just writing the same thing with different notation, this is E of X squared minus E squared of X, which is E of X squared. Right. Okay. And so theorem 6.2 and 6.3. This is theorem 6.2, the expected value of a random variable. And 6.3 is the expected value of a constant is a constant. So we use those two theorems in this proof. Okay, so the expected value of mu squared is mu squared. Okay. Okay, so we use that. Okay, so then theorem 6.6 is this theorem says that the variance of AX plus B is equal to A squared times the variance of X. Okay, so by definition of variance and the corollary, the theorem 6.4, we get, so the corollary to 6.4 was the one with the polynomial. Here was this one. No, wait, this one. Okay, so that's the corollary to theorem 6.4. So I'm going to copy that and bring this down here to remind you. So reminder. Okay, so that was corollary to theorem 6.4. And we have definition of variance. Okay, so with that, we get that the variance of AX plus B is equal to the expected value of, well, so you have the random variable AX plus B. And so the variance of that random variable is E of that minus the expected value of it, minus the expected value of it squared. Okay, so also a reminder, definition of variance. The definition of variance says that if you have the variance of a random variable y is equal to the expected value of y minus expected value of y minus its mean squared, right? So if you take the variance of AX plus B, if you letting y equal AX plus B, you get that the variance of AX plus B is equal to the variance of y, which is equal to the expected value of y minus mu squared, which is equal to the expected value of. And so here y is, here we're using the set here. So this is the set part. And so now the y is the AX plus B minus mu is the expected value of AX plus B. And you're taking that thing, that difference, and you're squaring. Okay. So I'm using definition of variance, and I'm using that the random variable in the definition is AX plus B. And so that's how I'm getting this expression here. Okay, so I just wrote that out, more steps there. So this is equal to the expected value of, well, you have the square of the set. You have the square of the set in there. And in the set, you have AX plus B. And then you have a minus A E of X minus B. Okay, so doing the algebra there, you get that. Okay, so in the set, the B and minus B cancel. You have a plus B and a minus B, and they cancel. So you're left with AX minus A times E of X inside the parentheses. So this is the expected value. This is the expected value of the A is going to come out. So you now have the A squared. So the A is inside the parentheses, and you're squaring the parentheses. So if you move the A out, you get A squared. And then into parentheses, you have what's left with is X minus E of X. And so now this is equal to, you can take the constant out of the expected value and get A squared times E of, and you have X minus E of X, and you're squaring what's in the parentheses. Well, the expected value of X minus E of X squared, that's equal to the variance of X. So this is A squared times the variance of X. So what we just showed is that the variance of AX plus B is equal to A squared times the variance of X. That's the theorem. Okay, and so now that's proven. Okay, so that's the proof of the theorem, and I reminded you of its corollary, and you showed how to use the definition of variance in the proof. Okay, so so the next section is 6.7 on Chebyshev's inequality. And so the first thing in the section is theorem 6.7, Chebyshev's inequality. Let capital X be a random variable if the expected value of x squared is finite. Then for any that's the end of a sentence. Let x be a random variable, period. If the expected value of x squared is finite, then for any c positive, we have that the probability that x is greater than or equal to c is less than or equal to the fraction e of x squared over c squared. Okay, and so that's Chebyshev's inequality. Okay, and so we're going to stop here for this lesson. And so let me just assign homework. So we went over homework 8. And so we're up to 6.7 now. And so for homework, this is what I want you to do. For homework, I want you to do, in homework 9, I want you to do section 6.4, 6.5.3 here, and 6.6. And we're not yet going to do 6.7. Okay, so the homework above that. So those 3 sections from homework 9. Okay, so 6.4, 6.5.3, and 6.6. So let me just write that out. So in homework 9, what I want you to do is the all problems from only these sections, from only sections 6.4, 6.5.3, and 6.6. Okay, so all the problems in those 3 sections. Okay, and so don't forget the announcements from the beginning of class. These announcements. Okay, so second exam is on December 9th, and the review for second exam is on December 7th. Okay, there's 2 exams and a final. Okay, so we're going to stop here. I'm going to stop the recording.